All right, so today 7.8, we're going to be looking at exponential models with differential equations. This actually ties back to where we started this unit. At the beginning of the unit, we looked at proportionality, directly proportional versus inversely proportional, and we wrote different equations. So our exponential growth and decay models derive directly from our, well, directly proportional situations. So right here, our directly proportional, we have the dy dx is equal to k times y. That is our directly proportional. If you remember, directly proportional is the k times y. Indirectly proportional is k over y. Those were the two variations on our proportionality. So dy over dx equals to k times y. And we will have that anytime we have something along the lines of the rate of change is proportional to. Our rate of change is proportional to. Those are the key words that we want to be looking for. And if we do, then we have that directly proportional situation. Now, what's nice about this, since that is always going to be directly proportional, then this leads us into having something that is always going to be our general solution for our directly proportional. So let's go ahead and find that directly, our general solution for our directly proportional. So dy over dx equals k times y. Let's start with our separation. How would we separate that so that we can then integrate? What would we do? Divide by y and multiply by the dx. So that means we should have 1 over y dy equals k, which k again is our constant proportionality, k times dx. Now we have separated, so we're going to go ahead and integrate. Let's integrate both sides. So what is the integral of the left side? 1 over y dy. What do we have? Natural log of absolute value of y. All right, and remember k is a constant, so what's the right side? Kx, k times x, plus c. Yes. All right, now let's go ahead and solve for y. So what do I do to each side? What's our base? E. So base e on both sides, and all this is in the power of e. So that's going to be the absolute value of y equals e, the kx, plus c. But what have we seen? If we have a plus, an addition or subtraction in there, what can we do? Separate it. So let's go ahead and do that. So I have absolute value of y equals, and what would be our separation? And z to the c, right? All right, but e to a c, e to a constant, what is that? Just a constant. Now, we theoretically could go ahead and put that as c sub 1, and we have absolute value of y equals e to the kx times, and then that becomes a different constant, c sub 2. Do we need to write the subs? No, but we can. All right, and then I can bring that to the front, so absolute value of y equals c e to the kx. And then how do we get rid of the absolute values? So y equals plus or minus c e to the kx, but plus or minus a constant, do we need the plus or minus? No, so that just becomes y equals, I was about to write my plus or minus, I just said we didn't need them. Y equals c e to the kx. And that will always be true if we have this directly proportional situation. So right down here, exponential growth and decay. So if given dy over dx equals k times y, then the general solution will always be y equals c e to the kx. That is our directly proportional situation. Which then gives us an exponential equation as our solution. And it will either be exponential growth or exponential decay. So problem number 1, we have if dy dx equals 2y and y equals 1 when x equals 0, then what is the value of x when y equals 3? It's a very good question, right? So, dy dx, what do we notice about this differential equation? That's the ky situation, isn't it? Directly proportional. So do I need to go through that whole separation and integrating and solving for y? No. What would be, so let me write this, lost my train of thought. Directly proportional, there we go. Directly, this is directly proportional. So what is our general solution? Actually, it would, yeah, it'd still be general. So what is our general solution, guys? Y equals, yeah, that's a good start. C e to the 2x, good. That 2 is our k, they've given it to us, 2x. It's a general solution. All right, so we have a directly proportional to general solution. And we are going to be solving for our c and for our x. So we have to solve for c first, and then we solve for the x that they want. To help you organize this, I recommend using a table of values. So we have some x and y values. We have 2 that they've kind of given to us. What's the first x and y that they give us? 0 and 1. And what's the other one? We don't know. And 3. So we're going to use the first one. This first one we're going to use to find our c. So I have y equals c times e to the 2x. So where does my point go? How would I use it? 1 equals, and what is 2 times 0? And what is e to the 0? So what is our c value? 1. So this is first. We want to first find our c. But with that, we can now write a particular solution. So we have y equals 1 e to the 2x, but we don't need to write the 1, so just e to the 2x for this one, right? Okay, so that's our particular solution, but that's not our answer. What do they ask us to find? When? So we are now going to use our second point. So we want to find x equals what when y equals 3. Can I now solve for that x since I now know my c? Yeah, let's go ahead and plug it in. Let's do that. So 3 equals e to the 2x. How would I go about solving that? Yeah, let's log it. It's an exponential, so we solve it with logarithms. So that's going to be the natural log of 3 equals the natural log of e to the 2x. All right, so what happens to that right side? Yeah, so I'm left with what? Can I solve for my x then? Divide by that 2, and so x is equal to natural log of 3 divided by 2. And if you gave that to me an answer on a free response type problem, I would totally take it. However, that might not be the answer in a multiple choice. So let's use some log properties to simplify. So, y equals natural log of 3 divided by 2. Dividing by 2 is the same as doing what? Oh, it is. All right, sorry. Dividing by 2 is the same as what? Multiplying by a half. Now, if I have a number outside of my logarithm, we have a log property happening here. What can we do with that number? Do what? Bring it up as a power. That was one of the log properties we reviewed. That was in 7.6 day 1 is where we did that review of our log properties. And there it is right here, that one. So if we have a constant or a number outside, we can bring it up as a power. Okay? So that was one of our log properties from last year. So let's go ahead and apply it here. So that means I can bring up the 1/2 as a power to the 3. So I get x equals the natural log of 3 to the 1/2. But what does it mean to be a 1/2 power? A square root. So you might see the answer as the natural log of the square root of 3. And that would also be true. Now this was a non-calc problem, but I'll go ahead and give you the decimal. So that is approximately 0.549. So we do need to be practicing using our log properties when necessary, because we never know what format they might give an answer on a multiple choice. Okay. All right. Any questions on problem number 1? Let's turn the page. All right, population y grows according to the equation dy dt equals k times y, where k is a constant, t is measured in years. If the population doubles every 10 years, it's going to be important information there, then what is the value of k? So they're not giving us our constant, they want us to find our constant. So dy over dt equals ky. That's directly proportional, so what is our general solution? I'll start it out. Y equals c e to the k times what? T in this case. We're using t instead of x. T for time. Okay. We're also going to make a table of values. It's going to be t and y here. Now, if we look at all this, they actually don't give us any time or any points. But it says population doubles every 10 years. Usually when we're dealing with exponentials, we like to start with t or x or whatever. We want one that is 0. Okay? Well, every 10 years, that means what would be my next t? 10. But what is my y for each of those? Well, let's go ahead and see. So if we have t equals to 0, we would have y equals c times e to the k times what? What is k times 0? And what is e to the 0? So when y equals c. So our y when t is 0 is our c. Do we know what our c is? No, we do not. That is okay. But I want you to notice a pattern right here. When our t was equal to 0, our y was equal to c. Was that the same thing back here? When x equal to 0, was our y the c value? Yes, it was. And that is actually always going to be true. Because if you look at this problem, if you plug in 0, what are you going to be left with? C. So your first point, that 0 is always going to be 0 in your c value. Always. We call this our initial value. That's what we called it in pre-calculus last year. In pre-calculus last year, we did the format, you don't need to write this, but it was y equals a times b to the x. And that a was our initial value when x equals 0. So it's the same type of idea. Okay? So let's go back down here. So how does that c help us? This will come in. All right. Well, what are we doing every 10 years? What did I box up there? What are we doing every 10 years? So what does it mean to double? What would, in other words, what would I have in my box down there? What was that? Oh, good. Second period, some people said c squared. Thank you, guys. Doubling, we multiply by 2, not square something. All right, 2c. This is doubling. Doubled. Okay, let's use that. So we're going to use our 10 comma 2c. So we have our equation, y equals c e to the kt, solving for k. Remember, that's what we're wanting to do. Value of k. So let's plug that in. That would be 2c equals c e to the k times 10. So what is our first step to solve? I can't log it yet. What do we have to do before logging? Isolate our exponential part. So what do? Divide by our c. But what happens when we divide by c? So does it actually matter what c is? Because in the end, they will cancel and are left with 2 equals e to the 10k. Same thing would go if we were at or told that it was tripling in 10 years. Then we'd end up with 3 equals e to the 10k. All right, I want you guys to go ahead and solve that from there. This is Calc Aloud, so you're going to be finding your decimal value for k. So go ahead and try that out, please. All right, ladies and gentlemen, what are we doing to both sides to solve? Natural log, right? Natural log of 2 equals natural log of e to the 10k. So natural log of 2 equals what? And then what do I do to solve for k? All right. When you did that, which one did you get? A, B, C, D, or E? A, right? There we go. Problem number 3. So we have non-calculator on problem 3 and problem 4. So problem 3 is going to be very similar to actually, let's see, similar to problem 1. So we have our dy dx equals 4y. That is directly proportional, so we should be able to get a general solution. If y equals 4 when x equals 0, then y equals what? So I want you guys to go ahead and try this one out. This one is really just finding the general solution. Shouldn't be too difficult. We go ahead and do problem number 3, please. All right, let's go ahead and do this. So we have dy over dx equals 4y. That's definitely a directly proportional. So since it is directly proportional, what is our general solution? Maddie, what would be our general solution since that's directly proportional? C times e to the 4x, yep, because 4 is our k. All right, so what they're wanting us to do, we have an initial condition here. We want to find our C value. So let's go ahead and do that. So we have a point 0, 4. So let's go ahead and use that. So y equals c times e to the 4x. How would that look if I use that point? Alex, if I use that point, what would that look like? Times 0. Good. So 4 times 0 is 0. What is anything to the 0 power, ladies and gentlemen? So what is our c value? So can we now write our particular solution then? So if y equals c e to the 4x, what is our particular solution? Y equals what? So what is our answer? A, B, C, D, or E? A. There we go. And actually, before doing any work, we should have been able to eliminate C, D, and E before doing any work. Because from this right here, we know that our general solution is a C, E to the kx, because it is directly proportional. So it's not going to be a C plus. C plus, that's not going to be the case, so it's not C or D. And then this one is not even exponential, it's a quadratic, so it's not E. So the only two viable options were A and B, where C was equal to 4 or C was equal to 1. Came out that C was equal to 4. So knowing this directly proportional kind of situation allows us to eliminate down to a 50-50, and then you just need to find your C with the initial condition. All right, any questions on problem 3? All right, problem number 4. During optimal conditions, the rate of change of the population of a certain organism is, here it is, what is it? Proportional to what? The population. So that is the rate of change of the population. So how would I write that differential equation? What would be my setup for that? It wouldn't be dy and dx. What would it be in this case? dp for population over dt, we're dealing with time, equals, it's proportional to the population. How do we write that? Let's look back at our unit 7.1, all the way back to the beginning. So let's look at some of these. Let's look at problem 2. So the rate of change of a function g with respect to time is proportional to the square root of g. How do we do that? K times whatever we're proportional to, right? That's what that proportionality means. If it ever says it's proportional to something, it is K times that. And actually, we have the same exact thing happening right here in problem 4. The rate of the population is proportional to the current population. P prime is K times P, or dP over dt equals Kp. We have the same thing in ours. So dP over dt is equal to what? K times P. It's proportional to the population. K times whatever. Proportional to is K times proportional to. All right, let's see what else it gives us. Let's see, at time 0, the population is 300. Okay, that sounds great. So let's do a table. This is going to be a T and P table. So time equals 0, population is 300. Let's see what else it says. At time t equals 24, the population is 1,000. So 24, 1,000. At what time t is the population 500? So now we have a question mark and 500. All right. I want you guys to try it. We are first, let me give you your outline. So first, find k. Now remember, since we're directly proportional, we can rewrite that as a general solution. What would be our general solution? P equals C e to the times t, not x in this case, but same position, right? So first thing, find your k. Actually, find your c. Sorry, find c. But you should already know it, but find your c. Second is find your k. And then third, find t equals what when y equals 500. So those are your steps that you want to do. Please remember, it is non-calculator, so you should not have any decimals anywhere. Okay? You are going to have some natural logs happening there, so leave answers in terms of your natural logs and use that as you go forward. All right, so go ahead and try that, see what you can do. We'll check in a minute or so to do a couple of those steps. All right, ladies and gentlemen, let's check in with our first part, finding C. So which point do we use to find our C? The first one, 0, 300. So here we use our point 0, 300. So that should be 300 equals C e to the k times 0. We use that one because anything times 0 is, and so our k goes away, right? So what does C equal? 300, good. So we now know that C equals 300. So P equals 300 e to the kt. What point would we use next? The next one. So now use 24, 1000 to find your k. All right, go ahead and keep going. We'll check in another minute or so. See what you got for k. All right, are we ready to check on our k? Let's do our k. So we're using 1000. So we have 1000 equals 300 e to the k times 24. So what do we do first to solve for k, guys? Divide by our 300. All right, so that, if we cancel out those zeros, should give us 10/3, correct? Equals e to the k times 24. I'm going to write that as 24k. All right, what do we do to both sides? Natural log it, so that should give you natural log of 10/3. Cancels out on this side, so I'm just going to go straight to 24k. And so then what do we do next? So k is equal to 1 over 24, natural log of 10/3. You could bring that in as a power and make it a root. You don't need to, though. Just leave it like that. So we now, from these two, we now have our particular solution. We know that P equals C is 300, E, and now I have this crazy looking K, but that's okay. I'll just put it all in there. ln of 10/3 times T. All right, we are going to use that now to find our T when y equals 500. So go ahead and use that. Hopefully you've left yourself some space to do so. I'm going to give myself some more space. Also, I'm just going to take a step here, guys. Be very, very careful that you are not canceling out this e and that natural log. You can't right now because of the times t right there. You can't cancel that out. So please don't do so at that point. All right, ladies and gentlemen, let's check in. So we are finding t when p equals 500 using our general solution that we have down at the bottom in black. So that's going to be 500 equals 300 e to the 1 over 24 natural log of 10/3 times t. And we're solving for that t. So what would we do first to solve for our t? Good. Divide by 300. That should simplify to 5/3. Are we good with that? All right. E to the 1 over 24 natural log of 10/3 times t. What would we do next? Natural log both sides. So that would be natural log of 5/3 equals. We have to do natural log at this point. Natural log of e to the 1 over 24 natural log of 10/3 times t. So what I said couldn't cancel, I said this couldn't cancel. That down there can't cancel. But when you go about solving, you want to get to the t, which is up in a power. So you're going to have to use natural logs to undo that power. That cancels out. Not this natural log. That one's still there. But these two cancel. So we have the natural log of 5/3 equals 1 over 24 natural log of 10/3 times t. You could bring it to the power. You don't need to. It might make it look a little bit more messy. What could we do with the 1 over 24 instead of bringing it as a power? We could multiply it to both sides. So I'm just going to go ahead and multiply it to both sides. So that ends up being 24 natural log of 5/3 equals natural log of 10/3 times t. We're almost there, guys. Now, before we say exactly what we do, I want to address this. I heard some people say, oh, I have a natural log on both sides. Don't I need to exponentiate both sides? No. Please don't do that. The only way you could is if you brought the 24 up as a power, and you brought, since that's times t, you brought the t up as a power. But then you would have a t up in a power, and you'd be back where you were, where your t is up in a power, and we don't want to do that. So don't exponentiate. Caitlin, you have a question? Split it up into subtraction log of 10 minus log of 3. Technically, that would take you backwards and away from where you want to go and make it more complicated. Because let's just think about that. If I had that, that'd be natural log of 10 minus natural log of 3. But then it'd be all of that times t. And you could distribute that in, but now you have t in two places and you're making it a little bit more complicated. All right, so I wouldn't recommend that. I keep them together. So what do we want to do? Just divide it. We have t times something. Remember, though it looks crazy, that is just a number. It is just a constant. So I have a constant times our variable. How do we get our variable by itself? Divide by that constant. Natural log of 10/3 on both sides. Please do not cancel out those natural logs. I'm sure I would see somebody like, oh, natural log, cancel, right? They're functions, not numbers. Please don't cancel them out. So t is equal to 24 natural log of 5/3 divided by the natural log of 10/3. Yes, we could put that into a calculator and figure out what that is, but that is our non-calculator answer. All right, there we go, guys.